we got to do is we got to apply the fundamental theorem of calculus, the derivative part, but with an added bit of complexity. The first way that they could add complexity to this is they could ask you a question like this one. So here's the question. They're saying find the derivative. They want you to find out what this is equal to. The derivative, they say this is the operator, right? It says find the derivative of whatever comes next. So this is saying find the derivative of this function here. And now in this case, the independent variable, that x, is the lower limit, which is no good. Normally we need it so it's the upper limit. So in order to change this, all you need to know is this fact about integrals right here. So the integral from a to b of f of t dt is equal to negative if I flip the limits of integration. So if it goes from a to b, then if I switch it and I put it from b to a, then it's just a negative. So I use that fact here, and then it's in a form that I could actually apply the fundamental theorem. So I could say it's equal to the negative of from 2 to x of e to the negative 2t plus sine 3t dt. And now it's perfectly fine for me to pull out the negative 1 from the whole entire derivative, because if it's a constant times this, which is just negative 1, right, times that. So it's going to be negative 1 times the derivative of 2 to x of e to the negative 2t. And this line might not have been so relevant for you, but maybe it's clearer if I write it. Some people, dt. Right? If I were looking for this, now it's clearer, because now I just apply the fundamental theorem right here, where the derivative of the accumulation function is just if I plug in the x to the top of the integrand. This is called the integrand here. So it's going to be negative 1 times e to the negative 2x, right? Instead of writing t, I just write the x. Sine 3x. And then you could distribute the negative 1 to get negative e to the negative 2x minus sine of 3x. And then you're done. You've taken the derivative, you use the fundamental theorem, and you just need to know this fact. Now, the other case is applying the chain rule to it. So, in the general case, right, you could be asked to find the derivative d dx of something that looks like this. A to h of x, where it's no longer just to x, it's to some function in terms of x of f of t dt. And here, you really just want to apply the chain rule, okay? You want to think of h of x as u, and then just know, what would you do if it were regular chain rule? Well, you would do f with h of x plugged in times the derivative of h of x. And maybe you could see it better if we said, instead of calling this h of x, we called it u, right? But it doesn't really matter. Then it would just be f of u times u prime. Maybe you'll see it more clearly as a chain rule in that situation, where we're sort of like making putting something as u, and then we're remembering to multiply by the derivative of u at the end, right? Like an inner function, right? This is the inner function, h of x, or u is the inner function. But it's up to you how you want to see it. I'm going to leave it as h of x when I do this example. So let's say I said d dx of, I don't know, the integral from 2 to, it doesn't matter, x cubed of, and then I'm going to put some crazy function here, sine e to the t, whatever, e to the t dt. So let's say I was tasked with finding the derivative of this. Let's say I was finding out what this equals. Well, what do I have here? So the whole thing is that I'm going to first substitute this upper bound, even h of x, this is some h of x, in to here. So I'm going to start with writing it as sine, this is just by fundamental theorem, e to the x cubed, right? Where I took that upper bound, and I plugged it in for t. But now I have to remember to multiply by the derivative of that upper bound. That's all that's changing here. And the derivative of x cubed is 3x squared. And then I'm just going to rewrite it slightly as 3x squared times sine e to the x cubed. And then that's it.